Hi everyone, welcome back to my channel. I am Abhishek Paudel. Today I am going to do a derivation from fluid kinematics. This is a derivation of a continuity equation for three-dimensional flow in Cartesian coordinate system. Okay, so let's proceed to the derivation. We have considered a rectangular prism as a control volume here, and which is a very small element, and it has a dimension dx, dy, and dz. You can see here. And let us consider the velocity component also, and the velocity component is Vx in x direction and Vy in y direction and Vz in z direction. Okay. So before starting the derivation, we must understand the mass flow rate. Okay, what is mass flow rate? So mass flow rate means mass divided by time. Okay, I am going to derive a small expression of mass flow rate here. So mass means volume into density by time. Okay, volume into density means mass. Okay, so volume by time means the discharge. So that is discharge rho into discharge q. Okay, so volume by time means discharge, and let's write it here. Discharge is equal to velocity into area into velocity. Discharge, mass flow rate. Okay, I will derive in a small expression which can be used in this derivation later on. So rho into velocity into area is the expression for mass flow rate. Okay, so you understand. So let's find the mass flow rate entering this space and leaving this space. Just likewise, mass flow rate entering this space and leaving this space. So we find out the mass entering, mass flow rate entering, and mass flow rate leaving. Okay, so let's find the mass flow rate entering ABCD phase. Mass flow rate entering ABCD, entering phase ABCD. Mass flow rate entering phase ABCD, that is rho into velocity. Velocity is what? In this phase, listen, this phase ABCD, this phase the velocity is Vx, parallel to x is Vx, into parallel to x, this space has an area. How much? Area here is dz into this one is dy, this is also dy. Okay, so dy into dz is the area of this space. This must be the perpendicular area. Okay, so we have considered the x direction. So what is the perpendicular area? That is this space dz into dy. Okay, so let's write the area dy into dz. Let's write this area dy into dz. So now let's find out mass flow rate leaving this phase EFGH. Okay, entering from phase ABCD and leaving the phase EFGH. Let's calculate the mass flow rate leaving the mass flow rate leaving phase. The leaving phase here, the mass flow rate entering is ABCD and leaving is E of GH. Okay, leaving phase E of GH is, so you have to write like mass flow rate entering, that is rho into Vx into dy into dz, and plus del rho into Vx into dy into dz divided by del x. In x direction you are the mass is traveling in x direction, so into dx. Okay, so this is how you do this. So the mass is leaving from this phase and travel the distance dx. This is a binomial expression in the x direction. Okay, so this is how there is a change of mass flow rate for a distance of del x. It is written like this. Okay, so now, so our purpose is to find out the mass flow rate that is retained inside this rectangular prism. If you do mass flow rate entering minus mass flow rate leaving, then you are going to find out the mass that has remained inside this prism. So let's subtract this one. Okay, so mass flow rate entering minus mass flow rate leaving, doing this operation. So let's subtract this and this. Okay, so now I am going to erase this. If you subtract that one, you are going to get, so mass flow rate remained inside prism through x direction is minus del rho bx dy dz by del x into dx. This is the mass flow rate remained inside prism through x. When you work out in the x direction, you are going to get the remained mass flow rate this much. Okay, now you can write likewise here in other axis. Likewise mass flow rate remained in y axis. Okay, so you don't have to find entering and leaving y axis, just you can generalize and say likewise. So that is minus del by del y. Okay, you are finding out the mass flow rate remained in y axis, so that's why I have done in del y into dy. Del y into dy. And what is the difference inside this one? This one is density rho, and velocity in the y direction is vy. We have assumed the velocity in y direction vy, and in y direction the perpendicular area is this one. Dx into dz is the area which is perpendicular to the dx into dz is the area which is perpendicular to the y axis. All right. So we have done likewise, and we calculate this expression. So you can perform the similar expression for this y direction also, but you can directly write this one also, like doing likewise. So the mass flow rate remained in z direction. Okay, in z direction. I have to write in z direction. So likewise, so you write like minus del rho bz, because in this z direction the velocity bz, and the area perpendicular to z direction is dx into dy. You can see here. Okay, so dx into dy is the area which is perpendicular to the z direction, and you have to write like dz because you are analyzing in the z direction. So del y. So these are the mass flow rate remained in x direction, y direction, and z direction. All right. So we have to add all these mass flow rate remained flowing through this rectangular small control volume of prism. Okay, so now let's add all these mass flow rate. Okay, so adding all these mass flow rate, that is, so total mass flow rate, let's write total mass flow rate remained in control volume. Okay, so that is minus del rho dy dz minus del rho bx into dy dz divided by del x into dx, minus adding all these here del rho by into dx dz into dy by del y, and another one is del rho vz, and the area is dx dy into dz by del z. These are the three mass flow rate remained parameters. I have added these all, and I take the common here from here. That common is dx dy and dz, dx dy and dz, and dx dy and dz are the common. And let's take the common and let's find the total mass flow rate. Flow rate remained in control volume. Rate remained inside control volume. Okay, so that is, let's take the minus common here. Del rho bx by del x plus del rho by del y plus del rho bz by del z and dx, dy and dz. These are the, the common thing. So now let's write this equation number 1. This is equation number 1 here. Alright. So now let's find out the mass flow rate remained in the total mass flow rate remained in another way. So if you consider this whole rectangular prism is a control volume, then you can directly say that total mass flow rate remained inside CB is also remained inside CB can also be written as mass by del m by del T. Okay, del m by del T. You can write like del m by del T. And you know that m is equal to volume into density into volume by del T. You can write like this also. So density into volume by T. So that is del rho by del T, and volume is dx, dy, dz. You can see the volume here. That is dx, dy, dz is the volume. Okay. So now this, let's consider this as a equation number 2. This is the equation number 2. We can equate these both parameters here, which is both are the total mass flow rate remained while passing through the rectangular prism. All right. So now I'm going to equate these two equations here. So let's equate these two equations, and I'm going to erase this one also. So del rho by del T into dx, dy, dz is equal to minus del rho bx by del x, del rho by del y, let's equate this two, minus common del rho bx by del x plus del rho by del y plus del rho bz by del z and into dx, dy, and dz. Right? You can cross this dx, dy, dz here. So you can take this in the left side. Del rho by del T plus del rho bx by del x plus del rho by del y plus del rho bz by del z is equal to 0. For the steady and incompressible flow, incompressible flow, three-dimensional continuity equation is this parameter is going to be 0 because for steady flow there is no time dependency. Okay. So and the density is also not varying. The density is constant for incompressible flow. You can take it out. So that is going to be del bx by del x plus del by del y plus del bz by del z is equal to 0. Okay, this is our equation of continuity for three-dimensional Cartesian coordinate system. We have derived this. Okay, so this is the three-dimensional flow. But for the two-dimensional flow, you can omit this parameter. That you can write like this one. Okay. So for the two-dimensional steady and incompressible flow, for two-dimensional steady and incompressible flow, and it will be del bx by del x and plus del by del y is equal to 0. This is a for the two-dimensional Cartesian coordinate system continuity equation. Okay, so in you can also denote this Vx as u and Vy as v also. You can write like this also. In z direction that is w, and in x direction that is u, and in the y direction that is v. You can write uvw also. Okay, so if you write uvw, the continuity equation would be continuity equation in three-dimensional steady and incompressible. Steady and incompressible. What would be? Just replace this Vx, Vy, Vz by u, Vw. Okay, del u by del x plus del v by del y plus del w by del z. This is a very very important derivation of fluid kinematics, and this is a continuity equation in three-dimensional Cartesian coordinate system, and this is particularly for a steady and incompressible flow. Okay, so thank you so much for watching this video, and keep in touch for another videos like this. Okay, thank you so much, and subscribe my channel also. Okay guys, see you in next video.